Okay, good. So today's plan is to talk about dynamic programming. Now, I could talk about this at different levels, assume that you've never heard of dynamic programming, and then tell you all the basics, or I could start at a slightly higher level where you're somewhat familiar with dynamic programming, you've seen it in some class, and you just want to get more expertise and want to solve harder problems. So I'm going to try and start somewhere in between. I'm going to assume that you've seen dynamic programming. Dynamic programming is appropriate when it's appropriate firstly for optimization problems. So problems where you want to either maximize or minimize some variable, some objective function, and there are some constraints that are given to you. In many cases, these kinds of optimization problems can be solved using greedy algorithms. And in some cases, the greedy algorithms don't work. And there are good reasons for it. You can easily prove that greedy algorithms don't work in some cases by just constructing an example where it fails. When greedy algorithms fail, often the only recourse you have is to use dynamic programming. Now, dynamic programming can be quite simple. There are simple problems that can be solved using dynamic programming, and then it can get progressively harder. So one way that I have used to look at these dynamic programming problems are what are called as one-dimensional, two-dimensional, three-dimensional, and even higher dimensional dynamic programming. The one-dimensional dynamic programming problem, a good example is something called the activity selection problem, or room assignment problem, or the textbook by Corman, Lyserson, Rivest, and Stein has a problem called the rod cutting problem. You're welcome to look at any of these. These are fairly simple dynamic programming problems, and pretty much dynamic programming is the only reasonable approach for these problems. And I'm going to assume that you've seen at least one of these examples somewhere in one of the classes. We can, if you want, we can go over one of them. But for now, I'm going to move on to a two-dimensional dynamic programming problem and work out how one approaches this, what is the general strategy, and while solving that problem, I will tell you a little bit about how dynamic programming problems are approached overall. So today's problem that we're going to look at is the LCS problem. And if I have time, I'll get to the 0-1 knapsack problem. If you've seen these, well, it might still help you to pay attention because there is a very systematic way to approach dynamic programming problems, and understanding this can be very helpful in solving more general dynamic programming problems. So let's start with the LCS problem. The LCS stands for Longest Common Subsequence Problem. So it's a string problem or a subsequence problem, and it's typically a two-dimensional problem. So let's see where my slides are. Yeah. Right. Here you go. So let me start with this particular problem. This says I'm given two strings. In this case, the two strings are coriander and creditors. And my goal is to find the longest common subsequence between these two words or between these two strings. A possible subsequence might be CRIR, because CRIR shows up in that sequence, in that order, in both the words. So so with this example, what you need to understand is that a subsequence doesn't have to be a set of characters next to each other. They can be anywhere in the string. The only constraint is that they have to show up in that order. Now, as you can see, it's possible that some letter shows up more than once, but you have to know which letter you're picking in each case. So when I say CRIR, the first R is the first R in coriander, and the second R is the last R in the coriander, and same thing with creditors. So you have to know which one you're picking, and you have to show that it's in the same order in both the strings. In this case, it turns out that CRIR is the longest common subsequence between those two strings, because we don't know of a way of finding 5 letters that appear in the same order in both these strings. Now, we want to be able to, given any 2 strings, we want a general algorithm that would help us to find such a longest common subsequence. And in this case, these 2 strings are of length 9. In general, they don't have to be of the same length. They can be of arbitrary length, n and m, and our goal is to still be able to find these longest common subsequences. So in order to figure this out, the dynamic programming approach says, the first thing that it says is, of course, the first thing is to understand the problem. We've understood the problem. We are very clear about what a subsequence is. We know that the characters don't have to be next to each other. We know that they have to be in that same order in both of them. Now, what we're going to do is to try and write what's called as a recursive solution for this problem. And so the first thing we're going to do is to write a recursive solution that's correct, but that may not be efficient. And then we'll go through a second step where we'll try and make the recursive algorithm non-recursive, and we'll make it efficient. And the way we'll make it efficient is by using a table to store some partial solutions, and those are going to be roughly our steps. But in all of this, when we write the recursive solution, we will get what's called as a recurrence relation, which is going to be the mainstay of dynamic programming approach. So when you think of dynamic programming, the thing you need to think about is a recurrence relation. Now, the moment you have a recurrence relation, you essentially have you can design a recursive solution. And once you have a recursive solution, there are some techniques by which you can make it non-recursive by using an array or a table or some memo, so to speak. So those are roughly the steps of the dynamic programming approach. So even though you may have seen this longest common subsequence problem and know how to solve it, I'm going to go through these steps to show you how to do this in a systematic manner. So our first step is either to write down a recurrence or to write down a recursive solution. Both of these are approximately equivalent, and you'll see that sometimes one is easier than the other. What we're going to do here in this case is to design a recursive solution. Now, here's the recursive solution. Remember, in order to solve a problem recursively, you have to do the following. You have to take the problem and write it down in terms of simpler subproblems. That's what a recursive approach does. So in order to write a recursive solution, sometimes we have to add extra variables or parameters to our algorithm so that we can call it recursively, but with slightly different parameters. So I'm going to assume here that I want to figure out the longest common subsequence, that's LCS, of 2 strings S1 and S2, and we're going to assume that they are of length m and n, which in our case, we're going to assume that S1 is an array of characters, and the first m characters are the characters of the string, And same thing with S2, it's an array of characters, and because it's of length n, we're going to assume that the first n positions of the array are the characters of that sequence, of that string. So, so given these two arrays, our job is to figure out which are the common characters that we want as part of our longest common subsequence. Now, here is how the recursive approach goes. It turns out that there are actually two possibilities. The way we're going to simplify the problem is we're going to look at the last character of S1 and the last character of S2. There are only two possibilities. Either those two characters are the same or they're not. Now, if they are the same, if the mth character of S1 is the same as the nth character of S2, then we've now managed to reduce the problem because we can get rid of that last character from both sequences, and we will say the correct value of the longest common, the length of the longest common subsequence is 1 plus the longest common subsequence in everything without the last character, which is S1 and S2, but with m minus 1 and n minus 1. Of course, this only works if the last characters are the same. Now, what happens if it's not? Because we don't know whether that's going to happen or not. If it is not, then there are two possibilities, it turns out. Since the last two characters don't match, we are going to have to, we can now reduce the problem to one of two subproblems where either we throw away one character, the last character from S1, or we throw away the last character from S2. So we're going to call LCS recursively either with m minus 1n or with mn minus 1. And this is essentially what our recursive solution will be. And by the way, this recursive solution is correct, except that we didn't quite write the terminating condition. It's not clean yet, but this is a rough start. And it turns out that this is actually pretty good. You can take this solution and turn it into something meaningful. Now, by the way, if you really were to write a recursive solution, we would have to add some statements here that says if m is less than or equal to 1, then do something. If well, in fact, you could apply the terminating condition to be if m is equal to 0, then return 0. If n is equal to 0, return 0. Otherwise, just carry on, right? Yeah?
Will the time complexity of this be 2 to the m times n?
Yeah, so the time complexity is going to be nasty. The reason is that you're turning one recursive call into two. Each of those will spawn off two other recursive calls, and it just will go crazy. So time complexity is terrible, which is why we worry about that later. But this is a great start because, first of all, it gives you a correct solution. It'll work, it's just that it's not fast. And it will give you a recurrence relation. So if you think of LCS as a function that returns an integer, which is the length of the longest common subsequence of the first m characters of S1 and the first n characters of S2, then I can simply write this down as a mathematical formula quite easily, and I'll show you that in one of the later slides. So even though this is not a perfect recursive solution, I didn't quite add some bells and whistles, I've got the heart of the solution. And I know that this will roughly work. So from here, where do I go? For dynamic programming, you start with this point, and then you say, oh yeah, if I were to actually blindly use recursion, that guy will most likely spawn off two recursive calls, which in turn will spawn off two more, et cetera, et cetera. So you're going to have an exponential blow up, which is not good. However, if you start to think about that recursion tree, you will see that it has some nice features. And what you'll see is that many of the subproblems keep showing up over and over again, and because you're doing recursive calls, the system ends up resolving those subproblems and recomputing those answers, even though it did that a few minutes ago. So that's where the trick is. Instead of resolving problems over and over again, we're going to store our solutions to the subproblems in a large table, and whenever we see the same problem again, we're just going to reuse those solutions. And what you'll see is that if you use the table carefully, your recursion simply becomes very, very simple. And at that point, you're ready to throw away the recursion and write a non-recursive version. And you'll see that time and time again, with every dynamic programming problem, this is the same thing that will happen. It won't exactly look like this, but the approach will be exactly this. All right, so our next job is to figure out, well, I already mentioned this. If you look at, so we can draw the recursion tree here. And what is the recursion tree? The recursion tree is the recursive calls that each of these spawns from that recursive call. So I'm going to, let me turn the lights on. So the video is only for the screen, or do you know what?
Yeah, I can move it.
You can move it? Okay. Let me use, should I use this part or should I go to the left?
Well, I can move it there, but
It's okay here?
yeah, that's perfect.
Okay. So I'm going to write this as LCS of m comma n, because S1 and S2 is common in all of these. I'm going to drop that. LCS of m comma n will give you one of three possibilities. It'll be LCS of m minus 1 n, LCS of m minus 1 n minus 1, or LCS of m n minus 1. These are the three recursive calls that get called from the program that we wrote. We don't know which ones of these. In some cases, it may be more than one. In some cases, it may just be one of them. It doesn't really matter. What we know is this recursive call can spawn off one or more of these other recursive calls. Each of these, in turn, will have things going on like that. If I look at all of these, they all have a common theme. And the common theme is that they all look like this. They all look like LCS of I comma j, where I is whatever the first variable, first argument here, and j is the second argument here. And this is going to be true for every possible value of I in the range of 1 through m, and every value of j between 1 and n. This is what we know. So therefore, there may be lots and lots of repeats, but this is pretty much all the subproblems that will show up anywhere on the tree. I have now characterized every node in this tree. Of course, this tree is just stupidly large. We don't need to go and look at all of them because there are only m times n different subproblems. And that's what we're going to exploit. We're going to say, even though this tree looks like it's exponential, there are only m times n different subproblems here, and that's all we need to focus on. And now, suddenly, the problem doesn't look like an exponential problem, and we can go and approach this. So what's next? So we've written a recursive solution that's roughly correct. And as I promised you before, the recursive solution essentially gives us a recurrence relation that says either LCS of I comma j is LCS of I minus 1, j minus 1 plus 1, which means this is going to happen if the last characters are the same, or if the last characters are not the same, it's going to be one of these two guys, which is LCS of I minus 1j and LCS of ij minus 1. These are our only two possibilities. And so we've written down a mathematical recurrence relation instead of the recursive call. So this is what I said earlier. You can either start with a recurrence relation or a recursive code. Both of these come from the same place, and they are roughly equivalent. And what we said here is that the number of subproblems are only m times n. So I'm going to just make a big table for myself and store the solutions of each of these subproblems as soon as I solve them. Once I solve them, I will never do it all over again. I'll simply reuse the solutions instead of going through solving it. And now it turns out that there is an ordering here that's not so obvious. This, in order to solve LCS of m comma n, I better have solved all three of these prior to it, because I may need it. I don't know which one I'll need it, so I need to have solved these before that. In order to solve these, I better solve the ones in the next level, and so on and so forth. So this recursion tree imposes an ordering of how these subproblems need to be solved. That's what's called as a hierarchy of solutions. This also means that if I want to fill up the table, I need to fill it up in a certain order. I can't just do it in any order I like, because there is a clear dependence of solutions. Now, in the end, here is a non-recursive version of the LCS problem, which is quite simple, it turns out. And it essentially uses the recurrence relation that we wrote down earlier. And you'll see this in a minute. It looks a little messy and complicated. So let me try and decode this for you. We know that m and n are the lengths of the two strings that we are given. So that's statement number 1 and 2. I know it's not well indented, but it's statements 3, 4, 5, and 6 are some initialization code. The array C is our table, the table of solutions of the subproblems we have already solved. Now, what we can figure out from here is that if we look at this table, remember the table looks like this, where we have 1, 2, 3 up to m rows, and 1, 2, 3 up to n columns. Each of these, so we'll call this the array C, and each entry here is for the ith row and jth column. We want to be able to fill up this table because each subproblem depends on some other entries. Now the question is, what do we need at the end? What we need at the end is LCS of m comma n, which in this case is the entry that's sitting at the end of this table, the last row, last column. Whatever that value is, that's our answer. But we know that this guy depends on a bunch of other things, which in turn depends on other things, and so on. And so we better fill up this whole table before we figure that out. And so now the question is, in what order should I fill these up? And it turns out that I could do it in what's called as row major order, where I take it one row at a time, and in each row I go from left to right. If I do it in this order, it turns out I never get any dependencies screwed up. So that's going to be our logic. And in order to do that, that's the statements 7 and 8 that says for I equals 1 to m, for j equals 1 to n, which means in a row major order, I take it one row at a time, and in each row I go from left to right. So 7 and 8 tells us that we're going to do this in the row major order. And then here are the the cases that we have to consider. If the ith character is the same as the j, remember, if we're trying to solve this problem here, it corresponds to a subproblem where I have the first string, but I only have to consider the first I characters, and in the second string, I only have to consider the first j characters. So I'm assuming that the rest of the characters don't even exist. So because the second string is of j characters and the first string is of I characters, I only have to check whether the last characters in those two strings are the same, which is the same as saying, is the ith character in the first string the same as the jth character in the second string? If they are equal, then the solution is simply the solution of I minus 1, j minus 1 plus 1. Otherwise, if these two characters are not equal, then it's going to be either c of I minus 1j or c of I j minus 1, and I'm going to take the larger of the two because I always need the better answer. So I check if this is greater. If it is greater, then I take Cij to be Ci minus 1j. Otherwise, it'll become C of Ij minus 1. There's a bunch of things in blue. I'm going to explain that a little bit later. So this is basically our solution, and it's correct, and it works. This is one way to think about this is that it's a non-recursive version of the recursive program that we wrote. Hey, David. So this non-recursive version does exactly what the recursive version did, except that we never end up resolving some previously solved subproblem.
Is there an advantage of doing it with a DP table over doing it with the recursive memoization?
Right. So the advantage is what I mentioned earlier. Here, many of these problems will reappear.
But if we use memoization, then if statement is
Sure. So you could take a recursive version and add memoization there and say, oh yeah, if I've solved this problem before and it's sitting in my memo table, simply use it. Then it's exactly the same. It works perfectly well. Yeah.
When I use the recursion to save memory in the stack.
Right. So you could use both the recursion stack and the separate table. These two together would work out just fine. Or you could unroll it and turn it into a non-recursive version.
The recursive will be going from the bottom up.
Correct.
And this is a top-down solution.
Correct. Yeah, absolutely right. Yeah. Absolutely right. So the nice thing is that the recursion, if it sees a subproblem here that it has solved before, it'll stop and it won't go down further. So that's the good thing about it, right? Okay. So that's the general idea, and you're perfectly welcome to either use a recursive version with memos or a non-recursive version that you figure out. Typically, I like to use the non-recursive version, but it's what you can train yourself with or what you're comfortable with, and both of these will work equally well. Sometimes you have to worry about the time complexity of the recursive version. If you don't put your checks properly, then it's possible that it could end up being somewhat inefficient. There is with recursion, you also have the additional cost of a stack and the recursion stack, which you don't see, which could slow down your code. So that's an unseen cost that is sometimes that adds to the efficiency of your program. So in general, if you see a recursive version that you can turn to be non-recursive, you want to unroll it and turn it into a non-recursive version just to avoid using the stack. And the non-recursive version, as you can see, has zero memory other than the problems that it has solved before. And it knows, because of the ordering, it knows that it'll never revisit the same problem, and anytime it needs a subproblem, it's already been solved because of the order in which you've taken. So that's the great advantage of this non-recursive version. And in general, many of these DP problems, it may be possible to design it in this manner, to design your non-recursive solution that has these properties. Okay, so let's see what's next. Oh, yeah, so in the end, you return what is in the last row, the last column. So that's C of m comma n. So I haven't told you what this B is, and you probably know this by now. In order to the array C only keeps track of the length of the longest common subsequence. It doesn't tell you what the longest common subsequence really is. If you want to figure out what the longest common subsequence is, then you have to work a little bit harder. And the way you do this work is you sort of go and look at C of m comma n and say, how did I figure this out? Did I figure it out using this condition, or this condition? And depending on what I do, you can figure out how to match the characters. And instead of going through that trouble, we add a little memo in our table. So we create a separate array called the B array, which looks exactly like the C array. So you can think of this as one sitting on top of the other, and it just keeps a reminder of which of these conditions you actually used in order to compute that particular value. Yeah.
Can we have that? Can we make that a 1D array where
you cannot make it a 1D array because in each, remember this table is a table of solutions to subproblems. And each subproblem has been figured out using one of these conditions.
But
and you don't need all these subproblems is really what you're saying, but you don't know which one you're going to need.
But for the sequence within the string, can we not just mark what character is part of the sequence?
No. Because this solution to this subproblem might use the second, the fourth, and the seventh, but this subproblem might use the second, the fifth, and the sixth. You can never be sure. So it all depends on whether this guy used this solution or this solution. And remember, based on this, what you see is that the solution to this subproblem depends on three things. It could depend on this, or this, and you don't know which one.
Okay, I see. And the B array is to actually get that subsequence between the two.
Exactly. Yeah, exactly. So yeah, there may be special cases, there may be special problems where what you're saying might work out, but in this case, I don't see it. So here the good thing is that you don't have to go back and do the backtracking all over again. You're keeping all the information as you do the work, and then simply reading off the answers. So in order to actually build the solution, you start here. If the B array says go left, then you know that it used that subproblem, and you can simply use the solution to that subproblem. If it went that way, you know it used this subproblem. If it went that way, then you know that these two characters matched, and you can spit that out and go to the other subproblem that needs to be solved. So the B array will tell you exactly how to reconstruct the answer.
So basically, if it's diagonal, that's the character you include in the
Correct.
solution.
So anytime you see the diagonal, that's when the match occurs, and that's your common character, and you spit that out. So the B array will essentially start at this end, and it'll tell you how to take that path and construct the common subsequence. So that's basically the idea. Here's an example. Here we use the string alphabet and habitat. And what you see is that there's an extra row and column that I've added, which has all 0 values. So what I've shown here is the C array, and you also see the B array, which is these arrows, which we saw in the algorithm. And the right answer is here. It says that the length of the longest common subsequence is 4, in order to figure out what those characters are, we know that the T matches with the T, so that says go diagonally. So the last character in your match is a T. You spit that out. Goes over here, that's not a match, that's not a match, that's not a match, that's not a match. So the next thing that matches is a B. And from here, A. And then here is the H. So that's your longest common subsequence, and you're done. So simply follow your nose with the arrows, and you get your longest common subsequence. And because this is 4, you know that there should be 4 diagonal arrows that you'll hit on the way, and those are your answers. So even though there are many other places where there are diagonal arrows, really the ones that are relevant are this one, this one, this one, and this one. Right? So you just, essentially you just read those off. And this should convince you that it's not enough to figure out, to just have a one-dimensional array of these.
Yeah.
Of
There's
these.
many more arrows. I thought
There are many more arrows, yeah, exactly.
So that makes total sense.
And by the way, there can be more than one answer.
Yeah, yeah,
Right,
yeah,
yeah.
yeah.
Right.
So using this, we're always going to start from the bottom, right?
Yeah.
And
So for instance, ABAT is also an answer, I think. Oh, sorry, no, no, it's not. AABT is also an answer. Is it? Oh, no, that's not true either. Okay, I take that back. There's only one answer here. In general, there can be more than one answer. So this is a classic example of how you methodically follow this dynamic programming approach. If you follow this, you won't make a mistake. Otherwise, there are a gazillion ways you can screw up. You can screw up on the recurrence relation, which is the heart of the problem. If you make a mistake there, you're sunk, because you're not even going to get your first recursive program to be correct. If you don't start with a correct recursive solution, you don't have much hope of actually getting a correct solution in the end. And then after that, there are a couple of steps in terms of figuring out the ordering. Well, first of all, because we wrote down the recursive solution, we were able to identify all the subproblems we needed to solve. Because of that, we were able to design the right table to store all our solutions. And because of this tree, we were able to figure out in what order we want to solve them in order to get all the, the one answer that we really wanted. So that's the approach. You can go and try other simpler problems first to see that this approach works for you. And we're going to now look at another two-dimensional problem where we use a similar approach. How are we doing on time?
we're 42 minutes in.
Okay, good.
Yeah.
Yeah. So then let me show you the knapsack problem. Okay. So let's start with something called the fractional knapsack problem, which is not, this is not the regular knapsack problem. The way I usually set up this problem is that there's a burglar who decides to break into your house when you're out vacationing on the beach, and the burglar takes a look around and sees n different items in the house, and immediately knows roughly their values. So we have n items with n different values, and what we're going to assume here is that these items have a quantity. So your house is not a regular house with with a refrigerator and a TV and your laptop and your desktop and your fancy watch and other things in there. Instead, it's think of it as a warehouse where you have a sack of bricks, you have a sack of gold bricks, you have a sack of some jewelry, diamonds, etc., etc. And the burglar can take any amount of any quantity of each of these that he or she wants.
What neighborhood?
Yeah. This is before Miami Vice, shall we say? So the burglar can take any quantity they want, and we also have there's a weight associated with these things. Of course, the brick is much heavier, and the gold is even heavier. And then there are some other light things. Maybe you also store some cotton in one of these bags. So they all have different weights associated with them per quantity. And unfortunately, this burglar only has a Toyota truck to carry the loot away. And this Toyota truck has a weight limit. It cannot handle more than X number of tons or whatever the weight limit might be. So because the burglar can take fractional amounts, the problem is a little bit different than whether the burglar chooses your TV or your laptop or the refrigerator. So how do we help the burglar to steal as much as possible from your house?
I was thinking we could sort by value and then by weight.
That's right. So it turns out the greedy algorithm is the right solution. So it pays for the burglar to be greedy. And what does greedy mean here? Obviously, the weight limit is a hard limit. It cannot be exceeded. So every amount of weight that you put in there, there should be an appropriate value for it. So what we're going to do is to sort the items by value per weight. But not value, but value per weight, right? Which is what, I guess that's what's given there. So it has to be commensurate to the weight. And so once we get that, then we, let's say your sack of diamonds are the ones with the highest value per weight. The burglar will load up the Toyota truck with the diamonds as much as possible. And then once the sack of diamonds are finished, he or she would move on to the sack of gold bricks and then move on to your sack of quinoa that might be sitting around. Yeah. Tastes good and it's healthy, yes. So maybe it does have a huge value at the time that this burglar wants to steal. And so he or she loads up the Toyota truck with whatever quinoa he can be found, and so on and so forth. So it's a greedy algorithm, very simple, and it works. So the only reason the greedy algorithm works is because this person can take fractional quantities. Okay? So then let's modify the problem so that it's not fractional anymore. This is called the 0-1 knapsack, which means either you take the item or you don't. So you have a refrigerator, you have a laptop, you have a desktop, you have a telephone, you have your Rolex watches and whatever else might be there in your house, and either the burglar decides to take the TV or not, either decides to take the refrigerator or not, and all of this is still contingent upon the Toyota truck that has a weight limit of some specified amount. In this case, it's B. So we do have n items. We do have each of those has a value, Each of those has a weight, but there's a weight limit of b, and the burglar is still interested in maximizing the loot. So the first thing you need to notice here, supposedly, is that the greedy algorithm doesn't work. Why is that? Well, if you were to do value per weight, then it says it may not work. Why is that? So the problem has to do with the fact that you either have to take it or not take it. So even though the value per weight may be the largest for one item, it's possible that it occupies a lot of space. And so let's say this is the Toyota truck. And let's say that I have one item that has great value per weight, and let's say it occupies this much of the Toyota truck's weight. What I could do instead is take two items with slightly lesser value, and maybe they are, but together they end up being larger value. That's where the problem is with the fractional case. So greedy algorithms don't necessarily work. So you might have a refrigerator with gold doors and such, but if it occupies the whole truck, that's the only thing that the burglar can steal. Instead, it's possible that by taking a whole bunch of different items with slightly less value per weight, the total value could be exceeded with the red items instead of the black item. That's what we have to kind of figure out. So greedy algorithms will fail, or there are lots of examples where it'll fail. So that's why you need dynamic programming, and this is where we have to start to apply our approach and figure this out. Okay. So in the remaining few minutes or so, I'm going to try and sketch out the approach. So what we're going to do is we're going to look at the last item. Now, there are only two possibilities. Either the burglar decides to put it on the truck or not. If the burglar decides not to put it on the truck, then we essentially have the same weight limit, but only n-1 items. Therefore, we have reduced the problem. That's good. However, it's possible that maybe the nth item should have been taken in the optimal solution. But if the burglar did take that item, then we still have only n-1 items to choose from, but now the weight limit has reduced because part of it has been occupied by this nth item. So therefore, what we get is a recursive solution that looks something like this. It says that if I have weight limit of b, and if I have n items to choose from, so let's call this k of n comma b. So I want to solve the knapsack problem with n items and with a weight limit of b. Then it turns out that there are two. In one case, let's assume that I do not take the nth item. In that case, I only have n-1 items to choose from, and my weight limit hasn't changed. Or I have to solve the other problem where I have n-1 items to choose from, but my weight limit has now changed, and it's going to reduce by the weight of the nth item. But this is not quite right, because by taking the nth item, I got some value. So what I'm going to do here is to add the value of the nth item. So either my answer is this or it's this, whichever is larger, right? And both of these involve subproblems, and both of these involve two variables where they're both changing. When I look at the whole tree here, I'll see that all my subproblems look like this. I've got k, I, comma, instead of b, let me call that w. Okay. So I'm going to assume that I have only I items to choose from, and my weight limit is some variable w. The only thing you have to remember here is that I started with n items. I called something as the last item, and I'm left with the n minus 1 item. So when I say I mean the first I items. So question is, how do I order the items? How do I label them? And I will argue later on. You can think about this, and what you'll find is that the order of the items simply doesn't matter. You can order them in any way you like. Simply label them as 1, 2, 3, 4, 5 up to n, and just apply it. You don't have to order it by value or by weight or by value divided by weight or anything of that sort. They will all work out fine. So this I simply means that in the labeling that I have, I look at the first I items, and that's all I can choose from, and my weight limit is some number w. So these are all the problems that I'm going to choose from. I, of course, can be any number between 1 and n, and w can be any number between 0 and b. So here, I'm going to assume that all the weights that we are associating here are all integers. If it's not an integer, my solution is not going to work. I have to do something else for that, and they have their own set of problems. So all the numbers involved are integers. Otherwise, my approach goes kaput. So these are the subproblems that I need to solve. This gives you the recurrence relation, and then I'm going to put it in a table. The table is now going to look different. Instead of C, I'm going to call it K. Instead of N, I'm going to go all the way up to B. Instead of M, I'm going to go all the way up to N. And otherwise, the problem looks the same. So it's still a two-dimensional table. And I can write, and I want this guy. This is the answer that I want. So that's when I get to choose from. When I is equal to n and w equals b, that's the problem that I want to solve. So pretty much all the pieces are now there. I have to write the recurrence relation next, and you'll see that it comes out quite easily. So those are my subproblems. Instead of k, I called it v. So let me let me fix that so that it's all consistent. All right, so this is k, sorry, v. Okay. And we want v of n comma b, and this says v of j comma l. So the arbitrary row is going to be j, and arbitrary weight limit is going to be l. And it says v of j comma l is one of two things. It's either j minus 1 l or v of j plus v of j minus 1 l minus wj. Those are all the things that came from here. Is that clear?
Yeah.
So that's your recurrence relation. It's the larger of these two. When you look at the table, it turns out that the dependence relationship is a little bit different from before. It only depends on j minus 1L, that's in the same column but previous row. So this guy either depends on this one here, or it depends on the previous row but some item somewhere here. So as long as the previous row is all filled up, you're going to be fine filling up the next row, which means that keeping it the row order is going to be perfectly okay. And so this tells us that I can do row-wise ordering of the problems, and that'll give me pretty much the code. I don't know if I have it written down. I don't, but it's very easy to write this. It says for I equals 1 to n, for j equals 1 to b, for j equals 1 to n, I equals 1 to b, write down this relationship, but I have to say how to do the first row and the first column. And usually it's helpful to add an extra row and an extra column and put zeros there. In some cases, you could perhaps do the first row, first column in some easy way and fill this up.
So this could be resolved top-down, non-recursively.
It could be done. It could be done recursively as well as non-recursively. The non-recursive version is what I just told you. Fill up the table in row major order and simply use this recurrence. Or if you want to do a recursive version, then you do this with the extra caveat that you never solve a subproblem more than once. That's it. Very, very simple. Typically, dynamic programming code is not that long and complicated. Wow. And you just have to, it's probably 4 or 5 lines of real code. The rest is all initialization stuff and so on. And that's it. That's the 0-1 knapsack problem. So this is called the 2-dimensional version. Next time I'll do one more round of dynamic programming. This time I'll do a 3-dimensional problem. That's the matrix chain problem. And matrix chain is still 2-dimensional. There's something called, there's the all pair shortest path problem in graphs, which is your classic 3-dimensional. That also is 2-dimensional, I think. We'll talk about this.
I think it is 2D.
Is it 2D?
We went over it. I think
Yeah, it is 2D. Yeah, it is 2D. That's true.
The indices are.
Yeah. So I am. What is my classic 3D version then? Here I say it's all pair shortest path. I have to rethink this. Maybe it's not. Yeah. Oh yeah, it is.
I mean, the table is.
Oh no, it is
right?
3D.
It is 3D
Yeah, it is
because
3D. But there's an efficient way of doing it.
because there is an additional variable.
Oh, yeah.
Yeah, it's a 3-dimensional. It's a 3-dimensional DP problem. So we'll talk about that next.
Is that the algorithm where it starts initialized with infinity?
Yeah.
Okay.
Yeah, and it's kind of instructive to understand that solution in terms of this DP framework and say, okay, let's start with a recursive solution, then let's talk about how the recurrence relation shows up, in what order are you going to solve them, et cetera, et cetera. So in general, the DP problems, you really want to be as systematic as possible, at least in the initial stages when you're trying to understand this technique really well. Solve them, be religious about following the steps, and then once you get the hang of it, then you can do whatever you very well please, because by then you're experts at it. So I think I'm going to stop here. Sure. So we'll do one more round of this DP problem. As I said, the all pair shortest path, and then after that, I'll solve some real problem. Maybe I'll pick 1 or 2 good problems and go through this. There are a couple of problems even in the textbook. There's a traveling salesperson problem version, and then there's an edit distance problem. These are all nice problems. We could talk about them. Or we could pick up a competition problem and solve. One of these, we'll figure out something.
So, and these two problems will be done Saturday? Or
Yeah,
is there one?
I'd have to find one, but I'm sure I can, yeah.